Then you get del V at constant temperature. You have no idea how I am going to measure this internal energy. Right? That was okay, you could measure, but it was trickier. Now you have all the apparatus, you can measure. In fact, such kind of equations where pressure, temperature, volume are involved, they are called equations of state. And if a thermodynamic quantity is involved, then it's called a thermodynamic equation, EQUA, equation of state, right? And there are some more equations like that. Maybe I'll give you the next few. Yes, please.
In the first lecture, we did that U is equal to del U by del T.
Right?
And now we have done del U by del S.
Yes. So, how many variables do I have? Yes. I was so hopeful on this linear algebra. How many variables do you have if you want to define the system? How many do you need to define? 2. Great. If I define 2, I know everything. Yes? Great. If I know temperature, I know pressure, I know volume. If I define temperature and pressure, okay, in this case, if you want to talk about Q, if I have volume and temperature, I know pressure. If I have everything, I know the value of U. Okay? S is also another variable in the same space. Let me talk a bit mathematics. Is also the same variable in the same, is another variable in the same space. If instead of temperature, volume, I could have as well taken S. Yes? So I can choose any 2 variables. H is also in the same space. All of these are in the same space. Any 2 variables if I take, they are all interconnected. So I will get to know all the other variables. Right? It so happens that entropy and volume, as we've seen from the combination of the first and the second law, the entropy and volume happen to be a more natural choice if I wish to decide about spontaneity. Happen to be a more natural choice for internal energy. Like temperature and pressure happen to be a more natural choice for Gibbs free energy. Okay, so now we have that, and for an ideal gas, you've seen that phi T equals 0. For a van der Waals gas, you could calculate P is equal to, just take everything on the right hand side, P plus, and you already calculated, great. Now, it's not just A, it's A by B square, that is next to B by square is because it's a volume, and anything on the surface. So somebody had asked me this question in this class or the morning class, I don't remember. Why B square? So if you think of the surface, then the area of the surface would come out as a square of its volume. Yeah, square of its radius. And therefore, this entire volume square is the one that you have to consider. But anyway, essentially what it tells you is the intermolecular interactions A divided by the square of the volume. That is per unit volume, how much is the interaction. If you go out, that spreads out more. So what is happening essentially is phi T is nothing but change in internal energy with respect to volume, temperature being held constant. So if I am going to expand the gas, all of these are positive terms, yeah? So if these are positive terms, my internal energy is going to rise if I expand the gas, and that's going to rise because my intermolecular interactions are now getting weaker and weaker. They're being spread over this entire big volume that is being created because I'm expanding the gas, right? That's what the physical significance of this particular result comes out to be. This is true, right? If I have less intermolecular interactions, my internal energy. Remember, I drew that potential energy surface. My internal energy is going to increase. It's a negative term, internal energy, right? So it's going to increase, go towards zero. So there are a lot more examples. We will go to some of them, preferably as tubes, as practice problems, where you can use these relations, these fundamental equations, and get to a lot of answers which otherwise would be tough. Okay, so we have some time, and then I can start focusing on the Gibbs free energy, because now you've already seen that if I know one of them, I know everything. I don't have to worry about it. So, mostly since you are doing everything at constant pressure temperature, so let's just focus on the Gibbs free energy. And let me write that back. dg is equal to dg dt p plus del g del p t dp. Yeah. So this happened to be minus s, yeah. This happened to be volume. Yes. Now, if you see the change of temperature, if you see the change in the Gibbs free energy with temperature, then it's nothing but negative of entropy, and entropy is always positive. So what we are going to discuss is dependence of G on temperature. So now entropy is always a positive quantity, so which means that minus x is a negative. And it's not that the other thing what you have to worry about is that for gases the value of S is much larger compared to that of liquid as compared to that of a solid. So if I were to assume that entropy does not entropy just varies linearly with temperature, let me just assume that, okay, for one substance, which if I say that if my heat capacity does not change much with temperature, so I can assume that. Let me plot G as a function of temperature. So for gases, it's going to be the maximum slope. So if I start for gases, it's going to be the maximum slope. If I do the same thing for liquids, the slope should be less. They're all negative slopes, and I hope I draw it correctly. In the morning I made a very funny situation, and for solids the slope would be even lower,